Okay. Now, let's talk dimensionality reduction. Okay. Now, let me do this. Let me try using pictures first, and then I'll go to the. So, welcome to the second half of this class. Now, I'll take you to the dimensionality reduction. And let me begin with drawing picture. Okay, right. Now, roughly speaking, and okay, let me show you what dimensionality reduction does. Remember, let's recall in terms of input output. Okay, let's say if you have x1, xn, and then some kind of label. Okay, you have something like this, right? Can you guys see it? It's not focused very well. It's focused, okay? Right? And if you have L, S is a function of x1, xn. Okay? So let's make this y. Okay. Right? Now this is supervised learning, right? This is supervised learning. If y were cats and dog, that would be labeling or classification. If y were a value, that would be regression on or prediction problem. Okay. Now, if you have x1, xn, okay, and you have a function that f of x1, xn, instead of giving an actual value from the data set, it gives you some sort of like a nominal 1, 2, 3, 4, 5. So this would be like a cluster name, right? I just name a cluster. Okay. So once again, this thing is just something that the machine came up with arbitrarily. The importance is that people or data pointed are similar, share the same label number. But the label number themselves don't mean anything. 5 is not better than 4. 4 is not better than 3. It's not an ordinal scale. It's just a nominal scale. Okay. Moreover, it's a nominal scale that the computer came up with arbitrarily. It's not, it didn't come from the data set. Okay. So that's what we did, right? That's called clustering, right? Well, let me write this out and say your data set, what if I have the data set x1, x2, x3, x4, m. Yeah, this is m dimensional, right? And what I want is a function that takes x1, xm, and gives you something like y1, y2, y3. Okay, I give you this. Okay. The important thing that you have to notice is that m is much bigger than 3. Okay. So here, I'm not giving it a label. I'm not giving it a value. I'm giving it a location. Okay, a location. However, like one of your friend came to ask, okay, get the point. This is dimensionality reduction from m dimension to 3. So that's smaller, right? And conceptually, you can see plot 3, right? Anyway, in theory, you can go m to n, and n can be 4. You can't plot, but it's still dimensionality reduction. So the point of dimensionality reduction is you take original point in m dimension, you place it in n dimension, which is much smaller. Okay, if it's so small that it's 3 or 2 or 1, you can show it on a plot. The point is, the key essence of the word dimensionally reduction is that n is less than m. That's it. N is less than m. However, that simplification means you lose all the meaning, because the original m can be some kind of statistic, population statistic. Okay, so this could be data of one country. X1 could be per capita GDP. X2 could be inflation rate. X3 could be land mass. X4 could be carbon dioxide emission, up to X50. If I do this dimensionality reduction so that this country is represented as 3 number, you are not going to be able to say what is the first dimension correspond to. It's completely artificial. It's completely artificial. Okay? So why would you do that? Well, a simple case would be, a simple answer would be, you can't plot 20 dimension, but you can plot 3 dimension. You can plot 2 dimension. You can plot 1 dimension. So just think of it as a very, very mundane objective. I want to show all the countries in the world. Every country has 20 statistics. How am I going to show it? In one picture, not 20 picture. I want to show in one picture where the countries are. So I make an artificial dimension. Let's say 2 dimension. So all the 50 dimension representing a country becomes 2 value, y1 and y2, let's say. The important is this. Countries that have similar characteristics will be close together. So you don't really care about, let's say, okay, y1 and y2, okay? So let's say this is y1, this is y2, okay? And this is Thailand, this is Peru, okay? And this is Bolivia, and this is Laos, okay? Right? What it means is that from geography lesson, Bolivia and Peru are very close to each other. Thailand and Laos are very close to each other. But if I don't care about geographic location, I care about socio-economic, 50 dimension. It turns out that Thailand is very close to Peru. And Bolivia is close to Laos. Close in what way? Close in dimensionality reduced sense. What do I mean by Y1? I don't know. So you give up that complete, you get completely artificial dimension. That's my point. However, you can see why this is nice. If you want to sort of like create like international forum based on socio-economic similarity, right? You would do this. And then you would say, okay, well, Thailand and Peru, right? Peru, I think I use Peru. Thailand and Peru and maybe Mexico, say, okay? And maybe I put Cameroon here or something. Should have dialogue because we face similar challenge in terms of geography, natural resource, inflation, GDP, wealth inequality, Gini index, all kind of stuff. We face similar kind of problem. So we should get together and sort of like do a homework together, how to run the country. Now, and then you have Bolivia and Laos and I don't know, Japan, whatever, okay? So this could be something like this. So you can see right away, right now, I'm actually already talking 2 major pillars of unsupervised learning. I reduce the dimension, then I do clustering. Okay? Actually, in real life, what's going to happen is most of the time, and this is my recommendation, I do clustering first, then I do dimensionally reduction. Okay? And that data set, okay, that I have your TA send COVID data is exactly that assignment. Okay, but okay, we're getting ahead of ourselves. I haven't talked about dimensional reduction yet, right? So let's go to dimensional reduction. So now you know. Now you know. So I could ask you a question. If output of the model is a label, and that label should be the same as it would appear in the data set, what did I just do? I did classification. Okay. Well, I came up with some model that takes data in 20 dimension and I represent it as a point in 15 dimension. Can't plot it, but still 15 is less than 30. What did I just do? Dimensionally reduction, right? So I can ask you, you based on the output alone, you can guess, what did I just do? What did I just do? Okay. Now, for all practical purpose, we're going to stick to lower dimension. Okay. There are not two, I would say flavor. Okay. So let's say I have data that looks like this. Okay. Looks like a cigar. Once again, think of that example I gave you earlier. People living along the river bank, right? Except I'm just going to make it simpler. Okay. Simpler, right? So right away, it's going to look like A. I'm heading from 2 dimension to 1 dimension. Okay. So this is one problem. Okay. Okay. Now this is like a cluster analysis, but I somehow want to do this. So you can think this one, right? We talked about it, so I'm just going to quickly do it. If I can find this line, I can just project everybody onto that line. And that's my address, 1 dimension. Okay. Right. Now that the line that I did earlier was even fancier, right? It was a curved line. This is a straight line, so it's even simpler. Okay. But same thing, right? So you used to have 2 numbers, x1 and x2 to locate. Now you just need 1 number because the projection onto this is just a street address. 1, 2, 3, 4, 5, 6. Okay. So this is 2 dimension down to 1 dimension in this sense. Now, this guys is kind of like a cluster. Okay. What if I say, okay, come on down, like you guys. Okay. This is x1, this is x2. I want everybody to come and line up at the front of the class. However, let's say you're sitting in groups. So this is project group 1, this is project group 2, this is project group 3. Okay. This is project group 4. This is actually, you see it right now, 1, 2, 3, 4. Okay. I say, okay, come to the front of the class, arrange by group. Now, if everybody just run forward, what's going to happen? You're going to be on top of one another, right? So what if I make an instruction so that this group comes over here, this group comes over here, this group comes over here, and this group comes over here, say. Okay. Does that make sense? Yes. Okay. It makes sense because you are closer to your groups. Okay. Now, it would make even more sense if the groups themselves, this group is next to this group because they are similar. So let's say, let's draw another picture. Let's say I have this group, I have this group, I have this group, and I have this group. Now, would I do this? Put this group over here, put this group over there like this? No, I wouldn't, right? I would put this group over here, put this group over here, put this group over here, put this group over here. So not only are students of the same group together, groups that are close together are also close together in 1 dimension. Does that make sense? Okay. I'm going to give you a shorthand for it. This one, I'm going to call it PCA. This one, I'm going to call it TSNE. I just name it just for fun. Okay. Now, let's see how it works. Okay. By the way, PCA stands for Principal Component Analysis. TSNE, you say TSNE. I don't know. People say TSNE. I say TSNE. T, stochastic neighbor embedding. Okay. But anyway, everybody call it TSNE. It's a technique. These two are very popular. Okay. There are other things that are also very good, but I consider these two representative of what you want to do. Okay. Once again, this kind of preserve kind of like distance in a clustering space. Okay. So you make artificial dimension that means absolutely nothing, because it's just lining you guys up along the front of the class, so that if you're from the same group, you kind of stand together. If you're from the same cluster, you stand together. If two clusters are close together, then they also find themselves close to each other, but in a reduced dimension. That's called TSNE in this case. Okay, there are other techniques that does this, but TSNE is, I would say, the most popular right now. This is different. This, guys, by projecting onto this, what's nice about this is that, well, what's not nice about this? What's not nice about this is that for most of the time, you kind of restricted to this kind of straight road. So you can't do very much fancy algorithm. You can't do that S thing. However, what's cool about it is that even though everybody gets squished onto one dimension, that one dimension keeps a memory of the original dimension. Right? Think about it. Because I have this line, right? You don't remember where you came from. Actually, you can. You can go back and say, original dimension, these are the guys that have high value of X1 and low value of X2. Okay? So you can imagine that this exercise about, squeezing Peru and Thailand and Nigeria and Canada into a lower dimensional space. If I did this, it's good. It keeps the clustering good. But I can't interpret the final dimension. Okay. Whereas this one is not as powerful. It only works with linear kind of a distance. But what's so cool about it is if Thailand and Mexico are close together, you can say why. It's because we are both high X1 and low X2 people. And the other countries are groups over here. Why are they close together? Yeah, they're close together because they are low X1, high X2 countries. So you keep kind of like information, right? So that's why, between these two extremes, they're both useful. And there are some techniques that try to, have the pro of one and not the con of the other. So they have pro and con. That's my point. Okay, let's do the first one. The first one is called PCA. Before I go to the data, I want you to imagine 3-dimension, cigar 3-dimension. Yeah? That's a data like this. Okay? Data like this. Now, obviously, from the previous example, what street do I want to cut? What street do I want to draw? I want to draw this line, right? Intuitively, why is that? Because it spread them out the most. Yeah, along this dimension, it spread them out the most. If I ask you, okay, fine, what is the other axis that spread the thing even out more? It's this thing. So that's 1, that's 2, and maybe there's a little bit of a pancake thing going. Maybe I should bring like a falafel or something. It's long. Think of something that's 2 foot long Yeah, a cigar, 2 foot long, or a braid, 2 foot long. It's 6 inch wide and 1 inch high. So it's kind of like elongated. So what is the direct, and I just take this braid, this piece of braid, and I stick it like that. So what would you do? You would take one line here. Okay, so this is the principal axis in which the braid spread out, right? And where's the second axis? It's the one that go the width, right? And what's the third one? This one. Okay. Why is this dimensionality reduction? Because after all, it's a 3-dimensional braid, and I reduce it to 3 number. It's dimensionality reduction because if I can do this well enough, I can ignore the last one. I can maybe ignore the last 2 and take just one line, right? So this is a dimensionally reduction insofar as you start with 3, you could end up with 3, but the 3 is ordered such that the first one has the biggest spread. The second one has a bit of spread left, and the third one has the other axis that spread. And they are orthogonal to each other. Okay, so you get from original 3-dimension to alternative 3-dimension. It becomes dimensionally reduction because if the data looks like a cigar, maybe you just take the first axis, ignore the second and third axis. You take the most important axis. What's the word for most important in English? Principal. Okay, and this thing is an analysis. So you got a P, you got an A. Well, the dimension 1, 2, 3, those are called components. So when you take the first or the first 2 or the first few principal, all this is called principal component analysis, PCA. Okay, analysis is what you do. You analyze data. Analyze data by breaking it down into component, but you don't break into any kind of component. You don't keep the original x1, x2, x3. You have y1, y2, y3. But because y1, y2, y3 are not any kind of random direction, y1 has the most spread, y2 has next to most spread, y3 has barely any spread. And then you just keep y1. Okay, so this become PCA. So PCA is what you do when you make the x1, x2, x3 into y1, y2, y3. But PCA done right, allows you to say, I'm just going to forget about y2, y3. I'm just going to get y1. So you reduce 3-dimension into 1 dimension. Now, just as you can reduce 3 to 1, you can reduce 20 to 15. But with PCA, you try to reduce it to just 1 or 2. Okay. In fact, if you add the word the principal, you mean the first one. So PCA is principal component analysis. It breaks down the original dimension into components, alternative components. So think of Y as dimension or component. But the principal, the most important is Y1. Okay? And if you project data onto Y1, you've got a 1-dimensional street address. So that's the gist of principal component analysis. Okay, now let's see how it works. Okay. Wait, something wrong? Okay, now I make this up. Of course, I always do. By the way, see, T-SNE, PCA, those are the 2 things. go to this page and you will see, you know, all the options and all the stuff, but I'm going to show you. Okay, let's do this. Okay. Now I make this up. And just to show you what it takes to make this up. I'm making binomial distribution. So that's bivariate normal distribution with mean 0 for each and standard deviation, sigma 1 and sigma 2. Okay. Now, this one is a correlation. It's 0. So it's going to have no proportionality. Okay. So let's say originally I say sigma 1 is equal to 0.8, sigma 2 is equal to 0.2. So 4 times as big. So you can think of variation along the x1 as 4 times. So this is what you get. Okay. Now, why do I need to add the word aspect ratio? Because normally Mathematica would just adjust the scale, right? And you wouldn't see anything because it would just be a square. Okay. So this way I just keep it like this. So you can see, right? So this is normal distribution. This is normal distribution. In fact, if I take this guy, and I do what we did before. Let's just take this guy, this random variate, and let's make it 0.8, right? 0.8, and this is 0.2, and I generate 1,000 of them, right? And what do I do with it? I make a histogram 3D, right? Of this guy. Histogram 3D of this guy. There. See? Or if I make a smooth histogram, I get this, right? Now, obviously, this one looks completely symmetrical because it's stretched. I didn't control the axis, so you can see why it's stretched, right? This is from -5.5 to +0.5. This is -2 to 0.2. So this should be more elongated if I didn't allow it to automatically scale. Yeah, so there it is, right? Now, I cheat a little bit, not cheat, but what I want to do is introduce correlation, right? Except I do a little bit of what's called change variable. This is called rotation matrix. Ask your friend from engineering what it means. But basically, I can control this. Instead of having it independent, I can have it rotate. So there's this guy. See that? You see that? So this is the first one. But now I rotate like this, uses an angle theta. This is my angle. Angle is pi over 3. So I rotate it like this using this rotation matrix. Never mind what that is. So basically, I take the blue and I rotate it up pi over 3. Okay, this is pi over 3. This is pi over 2. This is pi. This is 3 pi and a half. This is 2 pi. Okay, so now I'm just going to play with it with rotation matrix. So yeah, so I can play with this all I like, all I want. Oops, sorry, where am I? Now, yeah, so basically I can rotate the angle. Okay. Basically just moving the correlation. So I generate this data set. Okay, now I generate this data. Now let's skip all this all the way down to here. Here's my PCA. Where's my PCA? Where's my PCA? Ooh, I apologize. My PCA is in another notebook. Never mind. Okay. Well, what's going to happen is the PCA is going to be this line. It's going to look like a regression line. Okay. but unlike regression line, it's gonna give two lines because I have two dimensions. Okay, so one line is gonna go this way. What did I do with what did I do with my PCA? Okay, I haven't copied onto this notebook actually. Sorry, my bad. Okay, I just copied to this part where I generate data. Anyway, so okay, let's go to a TCA T-SNE like thing. This is my data, original data. Okay, this is kind of cluster. Remember I told you, if I tell everybody to walk forward, it's gonna look like this. It's gonna look like a mess. Everybody's just gonna be on top of one another. But if I reduce to one dimension, there's gonna be a big bit of a separation. It's this guy. Okay, so how did I do this? I use principal component. Okay, so basically principal component allows me to let's try this. Sorry guys, my apology. My PCA, it's supposed to, draw the blue line along the first component and the red line. I don't know what I did with it. I think I haven't copied it because it's in a separate note on PCA. But what I can do is show you this. Okay. When in doubt, sorry, let me just go to internet. That's easy. Okay. I'm trying to think, should I try to find it? Okay, let's assume I can't find it within the next 2 minutes, so I don't want to waste your time. Okay, here's what happened. Okay, here's what happened. You have the data set. Okay, you have the data set. And that data set is in whatever dimension it is. Okay, let's say it's in 3 dimensions. Okay, it's in 3 dimensions. And 2 dimensions. Let me tell you what. Now that it's not in Mathematica, I have to go back to here. My very bad. Sorry. So I have to stop this share. And okay, let's go back to paper. Put more paper, by the way. Okay. You saw just now, right? What I did was I created this data set. Right? If I were to do sort of regression analysis, I would just get one line. Okay, that's what I want to show. I would just get one line like this. Okay, but when I do principal component analysis, if the original dimension is 2, like in this case, I'm going to get 2 lines. Okay, so this is x1, this is x2. Instead of getting x1, x2, I'm going to get a new dimension called y1 and y2. That's what's going to happen. Okay, that's what's going to happen. So this cigar here, if I have 2 dimensions, I do principal component, I'm going to get this line, I'm going to get this line. Okay, and what's going to happen is this point used to have x1, x2 coordinate. It's now going to have y1 and y2 coordinate. See that? I need paper. Okay, this point, x1, x2, and let's say this is my cigar. Okay, This is my scar. What's this point, guys? What's this point? This is this one, right? X1, X2. Okay. Now, I take this data set. I call that function that you saw just now in the mathematical program called principal component, right? It's going to give you, in this case, 2 dimension. It's going to give you this thing and this thing. So now, how do I refer to this line? By this act, by this coordinate. Okay. Right now, I am basically prioritizing direction. So instead of taking x1 and xy from origin, I take y1 and y2 as a new coordinate. Okay, so PCA is a coordinate transformation exercise with the stipulation that the first dimension that you use is the one that maximizes the spread. And whatever spread is not taken care by the xy1, you do the same thing. You try the one that another direction that has maximum spread remaining. So you get the second component and you go to the third component, fourth component. Now, in this case, you go to second component and you stop because the data is in 2 dimensions, right? But if the data is in 20 dimensions, you have 20 components. Rank from most important, the principal, to the least important. Okay, so it's not dimensionally reduction yet. It's dimensional reduction because remember what we did before? Once I build this road, I don't really care about this axis. I just say, you know, where along that road. So this reduced dimensionality from 2 to 1. Okay, and PCA does this. PCA does this. Now, the reason I wanted to do this on Mathematica was there's one thing that's very nice that I taught you guys from, or I hope you guys learned from linear algebra. If this is a matrix, okay, of variance covariance, remember variance covariance matrix? For any pair of number, this is 6 1 square, 6 2 square, 6 3 square. Okay, and for those of you who did this, I hope you did this in statistics. So this one would be what? Sigma 1 2. Sigma 1 2 is equal to sigma 1 sigma 2. So standard deviation 1, standard deviation 2, and correlation 1 2. Okay, so any number, any pair. So if you have 100 data point, how many pair do you have? You got this matrix 100 by 100, right? You have the thing that pair with itself. So that one's going to have just the variance. Over here it's called covariance. Okay. Now this one you may shut your ears if you're not into it. But for those of you who did statistics, you should be into it. And those of you who are into finance, you definitely will have seen this. So this is the covariance between x1 and x2, right? Now, the whole thing here is a matrix. This matrix, if you do what's called eigenvalue decomposition, okay? Now, again, so a lot of you can just turn this off. Do eigenvalue decomposition. The eigenvector correspond to the biggest eigenvalue is your principal component. Okay. So basically, the reason I wanted to show you in Mathematica is to show you that PCA is not magic. It's really it's simple. Okay. So put it this way. I have this data. Right? This data becomes a matrix. This matrix here do eigenvalue decomposition. The first eigenvector or the eigenvector corresponding to the biggest eigenvalue will be y1. The second or the eigenvector corresponding to the second biggest eigenvalue is y2. Okay, and you can do this forever. You can do this until you finish all the So if you have 10 dimension, you have 10 eigenvector. And if you arrange them by the size of the eigenvalue, the first one is y1, the second one is y2, the third one is y3. Okay, that's why I wanted to show you that. Okay? Yeah, sorry guys, I messed up because I wanted to. I used to have like separate topics in different files, and what I do is put everything in one big thing called my textbook, and I haven't plugged everything in there. Okay, so it's I have to find it somewhere. So, but you get the point, right? You get the point that essentially principal component analysis came first. It's a way of breaking down into axis or coordinate that start from the biggest spread to the less spread. Find the direction of maximum variance. Okay. And once you found that, you have the second, the third, fourth, until you finish all the dimension. But if you only care about the first one, then becomes a first one or first two or first three, then becomes dimensional reduction. Okay. Now that is called dimensional reduction in that sense. At the end of the day, if I did this, okay, but instead of from 2 to 1, I start with 50 down to 2. Then I can plot all the country on a flat piece of paper, right? Because now Thailand will be close to Peru because based on this principal component analysis, Y1 value for Thailand is very close to Y1 value of Peru. And Y1 value for Laos is very close to Y1 value of Bolivia. Okay, so that's dimensional reduction. Now, T-SNE, if you recall, is doing this. Okay. Likewise, this is from 2 to 1, but I can just as well do T-SNE from 20 to 2, and that too will give Thailand close to, say, Peru. They will not give the same mapping. Why? Because the algorithm is different. Technique is different. The first one, principal component analysis, is useful for data that are fundamentally normally distributed, so to speak. If the underlying data set is normally distributed, then PCA would do a good job. The reason PCA has dropped in popularity is because with modern machine learning, neural network, and all kind of stuff, we work with nonlinear data set, data that doesn't have a normal distribution. It has kind of weird clustering behavior, maybe density based, all kind of weird stuff. Okay. So that in that case, something more algorithmic like this, okay, not based on calculating eigenvector decomposition, is more robust, I guess. You can use it in a lot more cases. That's why right now, if I say, what's the most, you ask all the data scientists in the world, what is the nicest dimensionally reduction algorithm you would like to use? They would say principal component analysis. But if you ask them, what do they actually end up using? They'll say T-SNE. Okay? T-SNE, algorithmically, I'm just going to give you very briefly what it does. The reason there's a T here is because they want to arrange things so that they preserve closeness. And how do you measure closeness? If you are close, this is how you say closeness. Okay? Ran out of paper? Never mind. Okay, so this is you. This is your friend. This is your friend. This is you. This is your friend. This is your friend. This is your friend. Okay? Let's say you are here. Let's say you're here. Okay? Now, you guys remember normal distribution, right? Normal distribution looks like this. right? Now, student T distribution looks like normal, except it kind of like the shape is flatter. It's not just bigger sigma, but the shape is flatter. So that's called T student T distribution, or just T distribution. Okay. So if you are over here, okay, now remember, this is a distance-based thing. How close are you close to this guy? Yes, you're closest to this one. Are you close to this? Yes, you are, but not so much as this one. You're farther away from this. How do I say, from your perspective, who is your buddy? I will draw a T distribution around it. And I say, well, of course, this is where you are. This is how close you are to this person. This is how close you are to this person, this coordinate. And obviously, this guy is not very close. This function is an assignment. It converts closeness here into score. So you can think of this as actual distance, okay? And this is kind of like emotional distance, okay? And then you align yourself in lower dimension such that you are closer to people with emotional distance close to you. And you just move it around. Again, this is an algorithmic thing. So if you run t-SNE twice, you might not get the same thing. Now, what's good about this is that it's very powerful. But what's bad about this is, again, in the new dimension, you don't have any meaning. New dimension just say who's close to whom. But unlike PCA, you can't say, oh, this is a high X1, low X2 kind of person. No, you can't. Because the assignment is kind of like this. It's kind of like everywhere, all over the place. Okay, so it's kind of like a mixed bag. Now, here's the deal. Today, okay, today, you have understood that this is an exercise that has no ultimate test of correctness, right? In a way, it's a way of organizing data so you can group them, you can get insight. And what are the two kind of insight? These are the two insight. One, who's around whom, basically. Okay? Who's around whom? Okay? Who is around whom? Okay? Who's around whom? Okay? So that's sort of like cluster. Okay? And how many groups? How many groups? Number two. Okay? Let's relocate everyone in new space such that if you are close in original space, you also have closeness in new space. Okay, so this is dimensionality reduction in new space of lower dimension. So those are the two things you do. Those are the two things you do. And again, next class, you will work with this data set, COVID data set. I'll tell you the game plan first, okay? But it's in mathematics. I know it's in mathematics. I just saw it just now, so don't worry. Yeah, maybe we should have done that today. What I did was I download the data from, I think, World Odometer, maybe World Odometer, or Our World in Data. OVID, yeah, Our World in Data.info or something. Okay, they keep, back then, they still do now, but nobody cares about COVID data anymore. But they have the infection rate, they have all kind of stuff, right? So I'll just show you real quick. The game plan is as follows. The game plan is as follows. Okay, this is called data analysis plan. Okay, I'm just going to run through quickly. You don't have to, you can't type in that fast. Anyway, so normally you would download live, which so right now instead of import.excel, it will be import from HTML. But because you have to do some cleaning and now that nowadays data is kind of not that interesting. What I did was I did this once and I sort of like freeze my day as of February of last year, right? So it's got a good decent size of data, okay? And I save it, I gave it to you guys. It's got 241 location, it's got 28 dimension. 28 dimension, okay? Now, what I want to do is analyze them, okay? But if I did this in 28 dimension, it's not much fun because I also want to kind of visualize a number of items. So for this example, I blocked out. So the way I did it was, this is the name of all the data set, all the data field. And I kind of blocked some of things that I'm not interested in. So I end up with, I think about 12 or 10 dimension, okay? Now, 10 dimension, you can't visualize them, except there's a way of visualizing 10 dimension data. It's called radial axis plot. So we'll show you that. So this exercise is going to have interactive visualization. It's going to have cluster analysis. It's going to have dimensional reduction all wrapped into one. Okay, so that's the game plan. I'll show you the game plan first. But anyway, so these are all the, distribution. So you can see that, maybe distance based would work because they all they don't have this kind of weird double lump thing. If it's weird double lump thing, maybe you need the that kind of a density base. But they all seem to be like a single lump kind of data. Fine. So did this, I did the clustering, blah, 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 blah. The idea here is that all these dimensions that I'm looking at, I can look on the axis plot. I can do the cluster analysis. And at the end of the day, it would look something like this. Okay. Now, this is the end picture. The end picture looks something, well, oops, sorry. The end picture looks something like this. Based on total deaths per million, reproduction rate, that's a rate of reproduction of the disease, vaccination rate, some other rate, population density. So these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 dimension, 15 or 16 dimension, okay? Based on 15 or 16 dimension, 240 countries. Find the cluster. Find the cluster. Once you find the cluster, I can't show all 240 countries, right? That would be messy. So each ring is the average within each cluster. And that average is called centroid. So I take 240 countries, look at 15 dimension, do clustering analysis, and I think came up with 7 clusters around the world. Each cluster, I take the average value of all the 15 and I plot it on this radar plot. And also, additional point, I make the thickness of the line proportional to the size of the cluster. Okay, so you can see that this is a big cluster. This is a smaller cluster. This is a tiny cluster. Just look at the thickness. Okay, again, this is mixing visualization and cluster analysis. And not only that, all these countries, I do dimensionally, once I do the clustering, right? So there's a country in purple, countries in brown, countries in green, countries in blue. Blue country really is a big group. It's a big chunk. Okay. That blue country in 16 dimension, all 240 countries in 16 dimension do dimensionality reduction into 2 dimension, plot them here. So this becomes dimensional reduction of the cluster of the 240 countries in 16 dimensions. Okay, so that's the game plan. That's the game. And you can easily do something like this for many things. And I've used this professionally for real project that, people contract us, my team to do, but obviously has not to do with COVID just for fun. Okay. But what it does, you can think of it as clustering and visualizing. So I can actually say, most countries are kind of like low in everything. There's a group that has very high reproduction rate. So that means a lot of high contagion. By the way, this data set, I remember, it's not that much fun. When I did this exercise, I think like a year earlier, maybe 2021, you get very interesting picture, like countries that, dies a lot, basically, okay? So a country that, once get infected, it's high death rate. And then there's some country that have high hospital coverage so that they get a lot of infection, but nobody dies. That sort of thing. Or country that has high population. Because if you remember, I don't know if you remember, in the beginning, you get high death rate along certain age group, very young and very old, or something like that, or, so you get some pattern, very interesting. After a while, most countries kind of converge into similar. So I think this data set was interesting, but I remember that it was very different. Different groups were very different. There was like Oceania, very small country that has no infection, but if you got it, you die, or something like that. I don't know. Okay, very interesting. So that's it. So this is, again, no label. You don't say good country, bad country, developed country, poorly. You just look at this. Once you've done this, then you can start saying, oh, this group are very good, nah? Because, hey, it's got a low infection rate and also low death rate, but it also has a high ratio of hospital beds per 100,000. Okay. I remember, I think Scandinavian countries seem to have a lot of beds. So, they don't have a lot of people and they have, they're a very rich country. So even compared to country like United States, they have very high ratio of beds, hospital beds per person. Okay, because they have small population, basically. It's a cold country. So anyway, and this is looking at this individual cluster, and I can, I can look at different, groups or something. Okay. So this becomes interactive. You can look and you can say, where is Thailand and all that. It's but the COVID thing, all that is done in a separate study. Okay. So anyway, I want to leave with that because next week, okay, your TA who's here is gonna repeat the stuff we did easily in Mathematica here, but in a maybe more ubiquitous way with Python. So what he's going to do is going to do, for example, with machine learning. I did ask specifically for him to focus on decision tree once again, because it's one of those things where if you can do it and it's accurate, you can get reasoning. Okay. So there are some Python library. Okay. So it's not like here you could just say method point to decision tree. There you have to say, okay, model class or something like that, but it's not that terrible. Okay. It takes a lot more lines, but it's doable within a Colab. Okay. So that would be that. And also, if there's time, he might take you through this in detail. Here, might as well do it in Mathematica because I already did it for you. But for machine learning, for supervised learning, I do explicitly want you to have experience working with decision tree in Python. Okay, because again, Python's a free software. It's everywhere. You know, you can be dropped anywhere on earth and somebody will have a Python notebook, right? So at least you should have that experience in Colab. So your TA is going to take you through that. Okay, so that should leave you about actually it leaves you about 10 minutes. Okay, so I really want you to spend a bit of time working on your data. Okay, you can look at past project. Now, I advise you to look at a few. Okay, so you go to internet. There's internet, right? And go to YouTube. YouTube. Okay. Now, what you have to do is search as a key term Basai key hyphen big data analytics. Now, it'll be something like autumn, something like 2020, let's say. And you will be doing the same thing. Once you do your project, you're going to be Basai / Big Data Analytics Autumn 2022. Okay, so you're going to have to do the same thing, except you'll be 2023. And because it's a group project, instead of having student ID, by the way, this is individual project. Now, just because it's on here, that doesn't mean they're all equally good. Some of them are very good. Some of them are terrible. Okay. So, some of them, even by a single student, is very good because originally I tried to pack everything in one course. Now I'm kind of making life a little bit easier for you by spreading this into data analytics, and then there's machine learning, there's artificial intelligence class. So I think you will have a little bit less dense material. Okay. And part of it is you have a group project. So look at this. So it's not just 2021. I think just 2020 was a good year as well, because there's one year where I think 2021 may not be very good because it was in the middle of 2020, I think, or 2021. I'm not quite sure, where everybody was online. So that year we didn't get to do much. Okay. So search for that, and that's what will be expected of you. Now, your life is, to be honest, a little bit easier than because back then I used to have this as single individual project, and everybody had to do everything themselves. Okay, so right. So sit in groups. I'm sorry, you were supposed to have like half an hour of 45 minutes, but stay on. Okay, so that's it for me. So next week, your TA is going to take you through like a more like a collab kind of thing, and then work you through. Okay, Kap. So I'll see you. I'll drop by next week, maybe.